hope it was an interesting to you as at least as it was for me. And Sam, I will let you lead the next session, our last session actually in this year.
Thanks, Raviv. Thanks for organizing this very nice discussion and the many questions that we received. This is an evidence about how important machine learning for our EDA. So thank you all. Today and now in the last session, we will have our last technical session, how to say. It consists as usual of, no, I mean, it's not as usual. It consists actually 6 talks, as typically we have only 5, but in the last session today, we will have 6 talks. As usual, every talk will have around 10 minutes, and then we have, sorry, around 5 minutes and plus 5 minutes questions as usual, and we would like to keep the last, how to say, remaining minutes and time slot for encouraging more brainstorming and discussions from everyone. I would like now to ask the first speaker for transfer learning for design space exploration with high-level synthesis to share his screen and start his pitch talk. Is the first speaker with us?
Hi, can you hear me?
Yes, we do.
Okay, great. Let me share my screen.
Yes.
Hi, my name is Jihye Kwon, and I'm a PhD student at Columbia University. Our paper is titled Transfer Learning for Design Space Exploration with High-Level Synthesis. This work was done in collaboration with Professor Luca Carloni. High-level synthesis, also called HLS, expedites the circuit design task and enriches the set of final implementations. An HLS flow takes in a high-level description of a target application design with a variety of knobs configured, for instance, loop unrolling or function inlining. A knob configuration directs the synthesis flow to generate a functionally equivalent but alternative implementation in terms of quality of result, also called QOR, such as latency and area. In this multi-objective design space, the designer tries to find the many Pareto optimal designs by applying different knob configurations. This process is the design space exploration with high-level synthesis, also called HLS-driven DSC, and is costly in time and resources. Here are a couple of examples from Spectre Benchmark Suite. On the top is application Sobel filter, and on the bottom is application merge sort. The two applications have different knobs defined and different ranges of QOR. With machine learning, we can train a QOR prediction model, say S for Sobel filter, using sample HLS results. However, even if the DSC results for Sobel filter are available, they cannot be directly used for training a new model M for merge sort, because the input domains and output ranges are different between the two applications. In this work, we investigate the following research question. Can we apply what was learned for Sobel filter to aid the DSC of merge sort? To address this research question, we present a series of 5 machine learning models. A single task learning model takes in a knob configuration and outputs a single metric of QOR, for instance, area. A multitask learning model predicts multiple QOR metrics, for instance, area and latency. Both of these approaches are for a single target application. Now, let's assume that we or some other designers have performed DSC for some applications, which we call source applications, and that those results are available. We first try to apply transfer learning. We train a model for a source application and transfer a submodel, the green piece in the square in this figure, to a new model for the target application. To improve the performance, we propose the multi-domain transfer learning model. This source model is trained using multiple source applications. in order to extract common knowledge across them. Lastly, we propose the mixed sharing multi-domain transfer learning model. This model includes an auxiliary sub-model for each application in order to emphasize the diversity among applications. We implemented all these models with fully connected neural networks. More details can be found in the paper and also in the uploaded presentation. Here, I'll briefly show the last model, the proposed mixed sharing model. Source model Q on the left is trained using DSC results of Sobel filter and BFS. For the target application, merge cert, a new model H prime reuses a submodel in the shaded box that's taken from the source model Q. During the training of the target model, the transferred submodel remains fixed. To evaluate the QR prediction accuracy, we use the DSC results from the Spectre dataset. We trained the 4 models for each of the 9 target applications in the dataset. This graph shows the geometric mean of test error rates for the sample complexity ranging from 1% to 10%. The blue graph on the top is from transfer learning without mixed sharing. This results in even higher error rates than the traditional single task and the multitask learning. On the other hand, this red graph on the bottom is from the proposed mixed sharing approach. This achieves the lowest error rates and thus the highest accuracy. To evaluate the DSE performance, we simulated the DSE by reading the QR values in the Spectre dataset. These bar graphs shows the distances between golden Pareto optimal designs and the designs obtained with each of the single task, multitask, and the mixed sharing transfer learning approaches. With 3% sample and 3% proposed designs, the proposed mixed sharing model achieves the lowest distance for most applications, and it also achieves the lowest geometric mean of distances. To wrap up, to the best of our knowledge, this is the first transfer learning approach for HLS-driven DSE, where different applications have different lists of knobs. The proposed mixed sharing transfer learning approach outperforms traditional approaches, and it can enhance the DSE at early stages or for huge design spaces. This concludes my talk. Thank you so much.
Thanks a lot. Very nice and exciting work. Of course, we have time for questions. As usual, you can ask on the Zoom and on the Slack channel. So you can also feel free to unmute yourself and directly ask. So please go ahead. Let me check the Slack channel. Nothing yet. Zoom.
I have a question.
Yeah, you have questions, please.
Looking at first, I like the approach very much, and I wanted to ask if looking at in slide 6, you have separate the unique layer, unique DNN, and the transferred or the common part of the DNN, and then can there be thought as a kind of an ensemble algorithm where the last layer of the network is actually responsible for balancing or setting the weights between the net that is unique for this model and the transferred learned net?
Let me share my screen again. Okay, sorry, it took me a little time. So
I think it was slide number 6, if I recall correctly.
Yes. So if I understood correctly, your question is whether the last layer is responsible for learning and balancing everything. The last layer, do you mean, can you?
So you have at the right picture, you have the pink network at the bottom, and
right.
You have the gray and the purple and the gray areas.
Yes.
So these
yes.
are actually two different nets that calculate something. And then there is the last vertical layer, and it looks like kind of two separate networks until the last layer. And this is
yes.
kind of can it be think of as an ensemble of these two networks, and the last layer is actually learning the balance or the weights of
yes.
these two layers.
Yes, exactly. That's correct. I did not go into the details during my talk, but there is a trainable parameter alpha t, where t stands for target, and this alpha is the parameter that determines the weight to give to the output from the gray part of the model, the shaded network on the top, and then the pink network on the bottom has weight 1, and it fundamentally trains two networks separately, but at the end, at the very last output layer, with the weight alpha, the two output values are combined. However, our intuition for having these two networks together is that if some properties that is specific to this target application can be captured by this pink network, then the gray network can process properties that are more common across all the applications and still contribute to the output value. And the final output, since we're going to perform gradient descent, if the final output and the real golden output are different, the difference will be back propagated, but we have this pink network on the bottom so that we expect this target application specific features or information to be back propagated through the pink network and not through this common network on the top. Does it make sense?
Yes.
Yes, for me it makes.
Thank you.
Okay, we can have time for very quick question. Just to remind the attendees that for the Slack channel, we have specific channel for the papers of today, the ML4 systems, so you can write your questions there. So I have very general questions. So when it comes to high-level synthesis and design space exploration, this is a quite, I would say, well-studied research area in the last, let's say, 10 years. How often machine learning has been applied there?
How often?
Yeah, how often people apply machine learning to do design space exploration for the HLS?
So there are some recent papers on applying machine learning for HLS-driven DSE, and according to their experimental results, applying machine learning helped efficient DSE, and they were comparative against the previous heuristic approaches. And in practice, in reality, I think machine learning can really help and be beneficial when the design space is so huge that we cannot use that other optimization or heuristic-based methods cannot make good performance.
Yeah, we have one.
Yes.
Yeah, sorry to interrupt. Yeah, please finish.
I just wanted to mention that in the papers, they calculate the average distance from the reference set. So in order to do that, they usually perform full exhaustive DSE and then compare the results against the machine learning based ones. And in order to do that, you first have to be able to perform fully exhaustive design space exploration. But when the number of knobs and values are very large, that is not possible. And I personally think that machine learning approaches can really benefit in those cases.
Okay, great.
That's
Thanks. We have one question from Luis, but I would like to keep this question to the end when we invite all speakers in our session today. So I would like to thank you again for the nice pitch talk. And I would like now to ask the next speaker for the paper using machine learning clustering to find large coverage holes. This is our friend Raviv, right? Raviv, are you going to present it?
No, this is Avi.
Okay, Avi. I mean, you are also
Yeah.
in this. Okay.
Okay. Yes. Sure. So hello again, and let's see. Okay. I hope you can see my screen. So again, welcome to beautiful Iceland. And I'm going to talk about using machine learning clustering to find large coverage holes, work done with Raviv and Giora Simchoni from our Department of Verification and Quality Technologies at IBM Research in Haifa. So what problem are we trying to solve here? So the way coverage is defined, at least in IBM, the designers defined very large sets of events of things that they want to see happening during verification. And then during the verification process, especially when we try to get for example, tape out time, we start looking at the events and see which events are not hit and try to generate tests that will hit them. And if you look at, you see here a list of a part of a report for one specific unit, and it's very hard to understand what's going on looking at this report. And this is very small portion of a report that can have thousands or tens of thousands of events. And it's very important to find large sets of events that has some commonality in them and work on them together, because first of all, they may hide bigger problems than just one specific point that we haven't covered. And also addressing many events together will make our life easier. We have some capabilities in the report. You can do some filtering and sorting and so on. And but this is not enough. So user usually export reports to Excel sheet, write some macros and so on, but it's still very hard to do. On the other hand, we have here a problem that we have groups of events and we want to separate them into something. So I guess this calls for machine learning. It can be clustering, it can be classification. So why not use that? And this is actually what we are trying to do. And our solution has basically 3 steps. First of all, we want to take those huge sets of events and try to cluster them into large groups of similar events. And we can have many measures of similarity, like the names of the events, signals that are feeding them, or many other different similarity measures. Then once we have those groups, we can look at each group and says, are there any large subgroups of events that are not covered? And for that, we can use unsupervised techniques, do clustering. And if we have a cluster that all of it is not covered, then this is something that can be important. We can use supervised learning, try to separate between the covered and the not covered event. And if we find here we find classes that are simple, easy to explain, this is again solve our problem. Or we can use other techniques that are specific to the group structure. And there are many techniques that are currently used for coverage, like a whole analysis for cross-product coverage. And finally, once we have that, we want to show it to the users. So what exactly are we doing? We're using similarity based on event names. We map the clusters that we find into cross products and then use known analysis techniques to do the analysis. So I'm going to talk about how do we find those clusters. So to begin with, we start with standard document clustering. Break the event name into words. Then we have something that looks like a document, and we can do clustering. We find that actually the place of word in the document in the name is important, so we add to the token the location, and this helps us. And then we can use many algorithms. We find that using the very simplest and fastest k-means with NMF to do feature reduction works very well for us, so we don't need to invest in a more elaborated harder algorithms. And again, in the paper and in the elaborated presentation I have, I talk a little about the different algorithms that we use. But this clustering alone is not good enough, because first of all, we find that the quality of those clusters is not high, even if we use the most sophisticated clustering algorithm that we use. And it very much depends on the hyperparameters that we use. And those hyperparameters need to be tuned for every different unit. So this is going to be a complex problem. And also, just finding the cluster is not good enough, because the user expects to understand why we have this cluster. They need explanation, and clustering algorithms don't provide this kind of explanation. And therefore, the solution that we use is to convert the clusters into a very well structured space of cross product, which means we find different dimension, each of them has values, and what we have is a cross products of all those values, and this is our coverage space. And there, the advantage there that this is something that is explainable. This is something that we have advanced analysis technique already available. So very quickly how it goes. We first find in any cluster locations of words that appears in all the events, like the first word in the events that you see here on the left is always register, so this is going to be an anchor. And also the word before last is data, it's going to be an anchor. And everything is between are the dimension of the cross product. We build the cross product based on that. And then again, I don't have the time to talk about it. We do some domain specific optimization to reduce the size and improve the density of this cross product. And we get to a nice cross product again for these toy 6 events that explore the space of accessing register in the processor. Once we have that, again, we can apply the analysis that we have and present the results for the user. And we are using that in all verification activities in IBM. They are part of our normal coverage status reports that we generated to user every day. It maps a large part, somewhere between 1/4 and 60% of the events into clusters. And many of them are large clusters, which means they contain large groups of events that are meaningful to the designers. And what's really important there, it's help them identify problems, both in the design and verification, help us speed up the coverage closure process, and therefore bring benefits to everyone. So to summarize, and I think one of the most important, I'm not going to go over all these bullets, is that machine learning alone could not solve the problems. Combining machine learning with domain-specific techniques with other algorithms help us find nice solution to this problem that can really help the team. And it's actually being used. And we are working to use it in other places, like the coverage directed generation framework that Raviv talked a little bit about it on Monday. So again, Iceland, and thank you.
Thanks, Avi, for the nice talk, and thanks for reminding us that we could be in Iceland. Yeah, that's a bit sad. So we have one question from Esma. So what does event coverage in this context mean?
Oh, event coverage is some event, let's say, I don't know, in the examples that I have here are a specific register in the design was accessed for a specific operation, or it can be I filled the buffer, or it can be I filled the buffer and 2 cycles later I flushed it. Those are things that are defined by the design and the verification team, or things that they think is important to see that happen during the verification to make sure that the verification is thorough, is effective, is thorough, is covering everything, and so on.
Okay, and we have also from here this question: what does the machine learning, the ML, try to learn and predict?
It's not trying to predict. We are using here the machine learning we are doing is unsupervised learning, so we are trying to cluster. We're trying to take a very large set of events, group them into clusters of events that has some commonalities, and we can extract structure out of it and then use it as a base for our analysis. So we are not doing any supervised learning. We are not using any prediction. We are not using any labels in this work.
Okay, thanks. We have maybe one more question, but I would like to keep it until the end. Otherwise, we cannot stimulate discussion at the end. So thanks, Avi, again. And I would like now that we move to the third paper, exploring logic optimizations with reinforcement learning and the graph convolutional network. So I'd like to ask the speaker to share his screen, and yeah.
Thank you. Can everyone hear me?
Yes, please.
Oh, hi. This is Mingjie from UT Austin, and I'll be presenting our work on exploring logic optimization with reinforcement learning and graph convolutional networks. So in this presentation, we'll be focusing on exploring the techniques benefiting to combinatorial logic optimization. In the combinatorial logic optimization step, the most widely used paradigm is to represent Boolean logic as standardized logic graphs. For example, AIG and MIG graphs. And then we use different operations such as balance, read, write, etc., to change the graph structure without alternating the Boolean logic. And in this work, we're using AIG, short for AND inverter graph, which is one of the most popular logic graph representations used in most academic synthesis tool frameworks such as ABC. There are also multiple graph operations available in the ABC frameworks to optimize these AIG graphs in terms of the number of nodes and logic depth of the Boolean logic circuit. And in practice, people often use a sequence of these operations to do the optimization. However, we still don't know what is the optimal sequence of these operations for different circuits to effectively, so in this work, we're trying to answer the question of how we can efficiently explore the search space of these sequence of operations to find a good optimization based on new circuit. In the original ABC synthesis framework, there have already been well-known heuristics of these operations, such as recent two operations, etc. However, the question here is the generality of these heuristics. Intuitively, the optimal sequence is probably design dependent. And in other words, different logic graphs would have different optimal sequence of operations. And in fact, in experiments, we observed that for lots of the combinatorial logic circuit, the baseline recent two is actually not the best sequence for optimizing these logic graphs. And so here we're trying to optimize these sequence based on the interaction between the ABC framework, which is very similar to the Markov decision process that allows us to use reinforcement learning for this process. So this process of optimizing logic Boolean graphs based on AIG graphs can be smoothly formulated as a Markov decision process. In each iteration, we can observe the AIG graph as the current state. And then we can choose graph operations as an action based on the current state. So the environment would then give us a new state based on the operation that we have chosen, resulting in a new AIG graph state observation. And so we can also obtain from the framework immediately how much we have gained as a reward based on the number of nodes we have trimmed down or the number of depth of the logic circuit we have optimized. And so by formulating the problem this way, the problem of exploring the operation sequence becomes a Markov distant process. And we can use our reinforcement learning algorithms, which is very suitable for solving these types of problems. One of the most essential, what we would obtain in the end is essentially a policy that chooses the best action it thinks it will do to achieve a best optimized circuit based on the observation of the current AIG graph. However, one of the most challenging points is on how we are interpreting the graph structural state. Because the graph representation of Boolean logic is usually extremely large, we naturally want to compress the state representation with some functional approximation. And in modern reinforcement learning, that's usually some either convolutional neural networks or neural networks, fully connected layers. However, unfortunately, these current reinforcement learning traditionally use these function approximations on Euclidean state distance, Euclidean state space. So specifically, normally they translate some vector representation with a fixed dimension in reinforcement learning. There have been already prior works that uses a fixed vector representation to represent the state space and use RL for logic optimization, published at EASCUS and ASP.DAC previously. And in this work, we're trying to use not only just these vector state representation, but use see if we can extract more useful information from the graph structure by leveraging graph neural networks. And so in this work, we use graph convolutional neural networks to extract the graph structural information from the AIG state graph. We choose a pretty simple graph network structure. The graph just sort of like a vanilla graph convolutional neural network. For each node, we assign a one-hot vector based on the node type. And then we use basically this vanilla graph convolution network to aggregate the neighboring information separately into each node. And then we, at the end, we want to obtain a single vectorized state representation for the entire graph by aggregating all the vectors of all the nodes in the graph in the complete AIG graph. And so this graph vectorization are also subsequently combined with graph statistics like used in previous work, such as the total number of gates, etc. And also we have included past actions that we have chosen previously. Obviously, including these past actions break the Markovian property, but we have found that to be important to, in our case, to have greatly improved the results. For more detailed results, we refer to the paper, but here I would just like simply to present a agent learning curve on the right. The black line is the baseline where we execute resync2 twice on the circuit. And you can see that the agent is actually trying to learn something. Basically, it starts far below from the baseline, gradually improves towards, and finally surpassing the baseline. Although I have to say that the performance still have a large space to improve, as you can see that variance between different runs and different circuits could be quite high. So in the end, we will also like to share some of our insights on the problem. We think that one of the critical issues left is to use this graph structure as to extract the effective state embedding from the graph structure. And also our current algorithms have restrictions on extracting dedicated logic hierarchies from these graphs. Furthermore, we have also included using some partial past experience as part of the state representation, which breaks the Markovian property. So that would be also something that could be improved. For this work, we have largely limited to our action space to discrete action space, but in fact, there are actually more enriched actions based on the ABC framework That it also involves parameterized actions, such as you can identify how many layers you want to, or synthesis, or basically optimize. And so in this work, we haven't included that in. Also, there are also room space for improving on multi-objective optimization, for optimizing the Pareto front of a number of nodes and logic depths, or also like optimizing the Pareto front based on timing and also area. Also, we have observed that RL is traditionally used for control problems, where here we are trying to use it for optimization. There have been some discrepancies in the target that RL is used for and what we want RL to do. And we believe that possibly there are also improvements towards the RL part, where more efficient space explorations could help also improve the results. That's all for the highlights. Thank you.
Thanks a lot. We have time for questions. Maybe I can start with one. How do you envision, this kind of optimization to be integrated within, let's say, the existing EDA flow? So how you would imagine now if you are one of those vendors and you want to take it and integrate it? So how you would do it?
That's a large question. I don't know if I'm supposed to be the person that answers it, but
okay, maybe some thoughts from you. I mean, how you would envision the integration of such a nice optimization. Yeah.
I think one of the challenges is that the end goal of these optimization could be very different and based on different designs and also the constraints from the designer. So I think unless there is a generalized solution objective that's indicated, that might transform into a well-defined solution. But for our problems, for most of the case, it's really the constraints are designed by the designers, and also different circuits might have different considerations. So I think that's one of the challenges on where that might difficulties that might block road from integrating a full ML-based solution to the framework.
Okay, interesting. Okay, any questions from the attendees in the Slack channel, in the Zoom channel? I have one more question. So I'm not sure if I missed it, but how did you obtain the data for the training?
Sure. So this RL algorithm is an online optimization. So actually the data is generated each iteration. Basically your ABC would give you a current state as the graph. And then basically you can also obtain from each operations the changes of how much you optimize. So sort of like for this user case, it's self-generated.
Okay, I see. Okay, so any more questions from attendees? Not really the case. Again, if someone have question later, so we can bring it at the end when we invite all the speakers again at the end of the session. Thank you. Thanks a lot. And now we will move to the fourth talk in our last session. AdaPool, multi-armed bandit for adaptive virology screening on cyber physical digital microfluid biochips. Very fancy long title. Okay, Mohamed from Intel.
Yes, thank you, Dr. Amrosh. Let me share my screen.
Please. Don't tell me this is Iceland.
No. I hope I'm in Iceland right now, but it's not.
Okay.
Okay, 1 second. Okay, thank you, Dr. Amrouche. Hello, everyone. My name is Mohamed Ibrahim. I work with Intel Corporation. This topic is a bit different from conventional CAD. It's mainly for platforms that are related to DNA diagnostics. So in this presentation, I will give a highlight on my work on using multi-armed bandits for enabling adaptive virology screening for cyber-physical microfluidic biochips. So by now, we all know that a rapid detection of diseases such as COVID-19 has become more important than ever. And we need more testing capacity in order to enable quick public health interventions, especially for diseases that can be asymptomatic. So in a typical diagnostic flow, we have a sample that is being collected, and then this sample, from this sample, we extract DNA, and then we amplify based on a specific gene, and then we do analysis in different ways. People can use, for example, electrophoresis or many different ways in order to identify the presence of some genes in the given sample. So the problem with this flow is that it's time consuming, and the time to result for such process can be long. Especially the amplification process. So in order to address this long time to result problem, researchers have tried different techniques or different tricks in order to shorten this time to result. One of these techniques or one of these tricks is known as sample pooling, where you have multiple samples that you extract DNA from, and then you pool all of them together under one PCR operation. So you can, in this case, you can save a lot of time while processing many samples at a time. So now if the pool's test result is negative, then this means all the samples are negative. But if the pool's test result is positive, then this means one of the samples or more are infected. So we need to do more testing to cover that. Now, of course, here the problem or the challenge here is that from our side is that the optimal pool size and the adjustment of operations that we need on any platform such as biochips is not known beforehand. We need to, of course, in order to provide a cost-effective way for a diagnostic platform, we need to know what is the optimal size, what is the optimal pool size. I mean, what is the optimal number of samples that we need to pull together in order to minimize the likelihood of having positive sample pools. So we don't have this information in advance. And therefore, we need to have a learning method that makes sample pooling adaptable to different infection distributions. And this learning method can adapt over time while we are feeding it more batches of samples. Of course, such a learning method can be implemented on the bench in a regular lab, but it can also be enhanced with integrated technologies such as cyber-physical microfluidic biochips, such as the one that's shown here. So this is one of the biochips. It's called Digital-Microfluidics. Basically, it can be used to, it can be programmed and it can be used to implement operations in a reconfigurable way. So we can use it, and there is an extensive amount of research on the synthesis and design automation for such platforms. And you can, I would encourage people to refer to the paper for more details. Now, for the proposed methodology, how we can use this platform and to enable adaptive diagnostics, we can have a closed loop system such as the one that is shown here. So this closed loop system consists of a microfluidic biochip, and this biochip has sensors or cameras, and then we have the reconfiguration software, which consists of the reinforcement learning method that we will apply and some synthesis framework that will translate the decisions into actions on the biochip. So the way this works is that we load in batches of samples. We take an action for sample pooling based on these batches of samples, and then we synthesize, and then we run the test or the diagnostics test on the biochip, and then we get the result. Now we get the result, we use this results to improve the performance of the sample pooling actions in the future. So we continue in this loop over and over again until we get to the until we let the system know the distribution of infection and then know the optimal pool size along the way. Now, of course, in order to implement this reinforcement learning method that we call AdaPool, because it's adaptive pooling, of course, we need to have a model that quantifies the quality of different sample pooling decisions. So this can be used even as a reward function in our framework. So of course, there are a lot of details of how we derive such a model that quantifies different sample pooling actions. I encourage readers to look at the paper for more details. But also a major advantage of using this formulation that we use to quantify is that we can also expect, or we can compute the expected optimal pooling strategy for a certain infection rate. So we can use that as a reference model in our work as well. Now, the problem formulation is that we have input biological samples. We constrain the throughput, the constraint, the batch size, the outputs, the optimal pooling strategy, and the objective is to enhance cost effectiveness by minimizing the number of positive infection pools. To do that, we use multi-armed bandits. So multi-armed bandits, it's basically an agent that allows us, that tries to select the arms which will maximize the expected rewards over time. So we map our problem to this multi-armed bandits, and these arms represented here as the sample pooling actions. And in our work, we tried policies such as epsilon greedy methods and UCB that the paper can has more details on it. So here is the algorithm AdaPool in action. So we have an example here where we have batches of samples over time. We have each batch has 4 samples. And then we have the pooling that we can do. We can do pooling for 1 sample, 2 samples, or 4 samples based on and each one of these pooling actions has a value that represent its effectiveness. So the first time we run this algorithm, we would select a sample pooling at random. So we do 2 pools. We pool 2 actions together, and then we have 2 pools together. We do 2 samples together, and then we run this. After we select these 2 pools, we run them through synthesis. We execute this on Biochips, and we get the result. So we now, since based on this selection of pools, we have this. The first pool is negative, so it doesn't have infection. The second pool is positive because there is a 1 sample here that is infected. So we use this information and feed it in the reward function that we actually derived based on the formal model. We continue in this process. So with this, and the second time, according to our closed loop system, we selected a pooling action. This time we can select 4 pools. We get the results based on the execution on Biochips, and then we apply in the reward function and so on. We continue, and we expect that along the way, the algorithm based on the multi-armed bandit formulation, it will converge to the optimal pooling size. Now, this is, I will go quickly through these results. Basically, this result shows the effectiveness of AdaPool. We have here the sample batches on the x-axis, and then the average reward. And then we have this line that shows the optimal pooling strategy. And then this figure shows that over time we converge both policies that we have chosen converge to the optimal pooling size, optimal pooling strategy. But of course, the UCB has a theoretical tendency to perform better at the long run. And we tried this at different distributions of infection. I'm showing here one example for this probability distribution of infection. And then the other one here shows how the different actions, different quantity, the quality or the values of different actions behave over time when we have such infection rate. So for such a low infection rate, we can pull more samples together. So we realized that we saw that over the way when we have more sample batches fit into the system, we see that the value of the action of pulling 3 samples together tends to have a higher value, which means that this is the better or the optimal pooling strategy compared to other ones. So in summary, I showed here quickly a formal model that we use to evaluate the effectiveness of sample pooling, and the way also to use this formal model in our AdaPool algorithm that can be applied in any closed loop system such as cyber-physical biochips. I also give briefly also a look at the selected results. Now, these results are based on synthetic data. We generate them using probability distributions, but the next steps would be to use actually real life laboratory data for further analysis, and also to create an end-to-end framework. We need to integrate this AdaPool framework with other synthesis techniques in order to have a complete end-to-end framework that allows more cost-effective diagnostic framework. Thank you.
Thanks. Very nice and exciting that we see how machine learning is applied for a little bit different area. And I don't see questions. Oh, we have one question. Okay, we have one question, but actually not related to the talk. Yeah, so I have one question from my side, but I would like to keep it until the end because we are running a little bit out of time. But anyway, we will, as I said, at the end of the session, we will talk again on all the talks. So thanks, and I would like now to invite the next speaker, automatic compiler optimization on embedded software through k-means clustering.
Hello.
Hi, please go ahead.
Okay, you can see my screen?
Yes, we do, please.
Okay, thank you.
Actually, we see not the other screen, not the...
okay, wait.
So you can switch the display there. Yeah, exactly.
I just duplicate here.
Love it.
Okay, this I have to remove. Okay,
Yes.
Thank you for your introduction. So my name is Michael Werner. I'm a PhD candidate of Technical University of Munich, and I work at Infineon. So I'm happy to present the paper Automatic Compiler Optimization on Embedded Software through K-means Clustering. We like to tackle in this paper, in this presentation, the problem of varying designs, varying embedded software for compilers. So we always have to configure the compiler dependent on designs. So, but first, I'd like to introduce the framework that we are using. So what we are facing is, so we see a shift from manual coding to coding of generators. And our approach is that we generate a design over different abstract layers. So first we have a specification layer where we specify a design, for example, a communication device such as SPI. Then we define an abstract layer in between, which is representing an abstract RTL design. And finally, we retrieve the hardware design, for example, VHDL or Verilog. And in between, we have now two different code generators or two different generators, one device specific one and one device generic. And the same approach can be also used now for the firmware flow. Of course, now we have no abstract RTL design, we have an abstract firmware design, and we generate also the C model. And now the idea is we can build a lot of different variants of a design. So the user is able to customize, of course, the device components, for example, the SPI or the core itself, but he can also define and configure the generators. And I like to show now some examples so you can customize the device itself, but also the generator. And there I want to focus now on these two aspects here. For example, he can define if the device drivers have to be generated in a driver specific way or in a generic way. So there he has multiple possibilities. And of course, the same also, for example, with hardware accesses, he can define if he wants to use macros, inline functions, or does he want to generate hardware accesses based on union structs. And dependent now on these implementations, also the compiler is acting differently. So, but first I like to give some background about compilers. So compilers like the GCC has standard levels, for example, 02, 03, and they are quite good starting point. And we also use a standard level, a starting point, but the compiler flags have also a lot of dependencies. And we resolve these dependencies by disabling flags. So we iteratively disable flags from such a standard level. And of course, a challenge in embedded software are the hardware-software dependencies, hardware-software interaction and also time dependencies. And we resolve this by including a verification step to check if the execution was correct. And we also have to simulate on a hardware simulator. So how do we add now this compiler framework into the existing framework? So we have different compiler configurations where we disable these flags. And in that way, we can generate now different binaries, which we execute now on our system. So in order to generate now such a training set, we have a certain specification, so a certain CPU core, and also a certain specification of the generator. But of course, we have different applications, so we can define different peripheral devices, and we can also configure the peripherals. And finally, we have these different compiler configurations based on the standard optimization level. So here in this presentation, I will show the example for optimization level 03 in GCC. And now we execute the binaries on the system and we measure costs. We measure the memory size and we measure the clock cycles, so the runtime. And we validate the correctness by assertions and conditions. So how do we integrate now our compiler optimization or how do we perform now this approach with k-means? So we try to identify now the disable flags with the highest impact on runtime and memory size. And we use k-means combined with elbow algorithm because of its simplicity, and we can easily adapt it to new core configurations or to new generator configurations. And we just need a small number of training sets since we use this generator framework, which is implementing and generating similar kind of embedded software. So I'd like to show you some results of the approach. So we measured now, or we optimized for memory size for the runtime and a trade-off between both. And in the first row, you see now the elbow algorithm where we identified the number of clusters, followed now by the clustering. And you see now in the achieved optimization of the memory size, we achieved an optimization of around of about 21%, in the runtime 3%, and trade-off almost 2%. So, and I'd like to conclude now this talk. So we can achieve with this approach our optimization beyond the given compiler levels of GCC. We can reduce now the cost for future applications which use the same core, the same configurations. And we can easily adapt now this framework to new CPU core configurations, to new generator configurations, and also to new compilers. So thank you for your attention, and please feel free to ask me.
Thank you, thank you. Actually, it's interesting because typically compilers problems are tough to be solved, and getting an optimization that goes beyond the standard level, how to say, indeed impressive. So we have time for questions. I can start with one. What are really the main challenges, and or challenges and limitations, or maybe let's focus on limitations. What would be the limitation for such ML optimization for compilers?
So the limitation, so the limitation is based on, so how do you specify the limitation here exactly?
So for instance, now if you want to, it's very easy, like what you said here, to move between or to adapt it between different CPUs. This is easy. Where it would be difficult, and if it's no limitation or challenges, then I would expect it to be adopted in all systems or to be in new feature in compiler, how to say. Um, yeah, I'm just wondering what could be the challenge if a such optimization would be really integrated inside the optimizations in the compiler.
Yeah, okay, the limitations are based more on this framework, since you have to perform now this training set generation for different configurations. So if you change the instruction set of the core, for example, then you have to run it again. If you now have different kind of implementation style, you have to run it again. So these are the limitations, but the approach is the similar one. And of course, maybe you also have limitations if you consider now different costs. So currently in this approach, we consider the cost of memory size, we consider the cost of performance, so clock cycles. But what happens if we have maybe also power, if we consider not just memory size in general, also maybe ROM size and RAM size. So this could be maybe some issues also.
Correct. Indeed. Okay, so we don't have questions on the Zoom nor in the Slack channel. Okay, thank you again. And we move now to the last talk in our session, footprint classification of electric components on PCBs, printed circuit boards.
Hello.
Hi.
Okay. Can you see my screen?
Yes, we see and we hear you. Please go ahead.
Okay. Hello, everyone. I'm Mingjie from National Tsinghua University, Taiwan. Today, I'm going to introduce our paper, which is collaborating with Yanzhi Wang from Footprint Crew and my advisor Zhongyi Ho. Our topic is footprint classification of electric components on print circuit boards. In case that some audience do not know what PCB and footprint are, let me introduce PCB and footprint first. This picture shows a PCB that consists of electric components and the bare boards and the footprints here. Footprints record lots of information such as border line, soldering pins, and lots of other information that used for PCB manufacturer to mount components on PCBs. So when PCB manufacturers need to mount a new component that they have never used before, they will need to design footprint first. Each component belongs to a package due to their function or pack materials. Here are some examples of 4 packages of components. Those trip resistor components are small and 2-pin in the left-hand and right-hand side. Compared with SOIC components, SOIC have lots of pins in 2 sides. It's easy to recognize them. And the DFN do not have lead pins, which can be smaller than SOIC. As for connector, they connect to other devices like SD card and cables. Since those packages are different, the way to decide the footprint of every package will be slightly different. To decide a footprint for a component, we need the method to decide the footprint, so-called footprint design rules, and the specification of the component. Since the machine and the environment of every PCB manufacturer are different, footprint design rules will be also different for every PCB manufacturers. Footprint design rules contain information such as length calculating, pad shape, and other necessary information. However, current footprint design works rely on experiments engineer follow the design rules step by step, which make it a time-consuming work in the design flow. For example, engineers read the specification and follow the design rules. They will know how to draw the outline of the footprint. And they read specification to find out pin information and follow the design rules. They can decide the shape and the location of every pin. Since this component can be plugged in, an entry mark and a line of PCB board's edge are needed. Finally, draw all the information that needed. A footprint is accomplished. To accelerate the design process, PCB manufacturers usually outsource footprint design to ODM companies, such as Footprint Cool. However, some manufacturers usually did not record the design rule as rule guidelines, but in engineers' experience. Therefore, manufacturers can only provide ODM company with footprint and specification libraries. So ODM company need to find out design rules by analyzing those two libraries themselves. So footprint classification is used for classifying footprint library into their own package to help rule analysis of every package. Otherwise, ODM companies have to classify the library by human, which consumes lots of time and money. In the process of footprint classification, there are three kinds of challenges. The first kind of challenge is that two packages are similar, but they can be classified by specific features. The second kind of challenge is two packages are similar, but they cannot be classified by footprint information only. And the last kind of challenge is that some packages do not follow specific rules. For example, in the first kind of challenge, the only difference between those two components is the location and the length of pin, which is not obvious. Thus, a significant feature is needed to recognize the difference and classify it correctly. And the second kind of challenge is that those two footprints looks almost the same, but they belong to different packages. It's extremely hard to recognize their package by footprint information only. The last kind of challenge is that those three components belong to connector and other packages. Since they have many different functions, those two kinds of packages do not have regular appearances. Connectors such as example A and B may connect with a SD card, USB, net cable, or other things. On the other hand, components such as GPS tracker, gyroscope are all different, which do not follow specific rules. So those components belong to type other. To solve those challenges, we propose our method. This is our overall architecture. We take the footprint information and the file name as the input, and the output will be the mapping of packages and footprints. Footprint classifier is based on XGBoost algorithm with 12 extract features. Half of the features are basic parameters of the component. Other features are from our observation. As for the part of file name classifier, we calculate word frequency using term frequency inverse document frequency TF-IDF, and a CNN is used as the classifier. The final prediction relies on evaluating the difference between predictions of two classifiers and the input component. This is our experimental setting and result. Our dataset contains 1,562 label data with a total of 20 packages. The average accuracy of our methodology is 94%, which is better than other baseline methods. And this is as our expectation, that in some cases where the footprints are hard to recognize, FileNets help to increase the accuracy. And if you want to know more detailed information about the experiment, please refer to our paper. And we go to the conclusions. We propose a methodology for PCB footprint classification. We adapt both footprint information and footprint file names to predict its package type. Through the proposed methodology, we can classify footprints with high accuracy so as to achieve footprint design automation and accelerate the design process. Thanks for your listening.
Thank you very much. We have time for question. Okay, so I have one regarding to the training data. So how this training data or how the data has been extracted or obtained, is those from realistic designs or just kind of hypothetical data used only for the purpose of the training? Or can you comment on the data itself that has been used for training?
Our test data is from the customers that provide to us, provide to the footprint group company.
Okay, so realistic data from real designs. Okay, I see. Okay, good. So we can now start the joint, how to say, questions for all the speakers in this last session. So I would like to ask all the speakers, the 6 of them, maybe turn on your camera and mic. And if someone has any question, please feel free to write it directly on the Zoom, unmute yourself, or use a Slack channel. I see, like today is the last session, there is a clear reduction in the number of questions, so we used to get more, but still good. We have already 2 questions to the first speaker, Jihye Kwon. So the first question is from Louis. He's asking you about which parameters or features from the design are you using?
Yes. Can I share my screen for a while?
Indeed, please.
So we are not using any feature of the high-level design. The model takes in only the knob configuration. The HLS flow takes in the high-level specification and the knob configuration, where our model just takes in the knob configuration. So for instance, here model S for software filter takes in a vector of 8 elements, each representing a value for block dimension X, block dimension Y, and so on. And our model takes the high-level design itself as a black box.
Okay, interesting. So there's no specific features are used. Good. So we have another question to you as well. We got it on the Slack. Did you evaluate how much data you can save when using transfer learning compared to training from scratch on the target domain?
Yes. In this experiment, we trained 2 models from scratch on the target domain, namely the single task and the multitask. And we applied 2 transfer learning approaches, one with mixed sharing and one without. And this result shows that to achieve similar error rates, the single task and multitask models have to use a little more samples than the proposed mixed sharing transfer learning approach. It's only a few percent of the design space here, but we think that this difference may increase if we can play with much larger design spaces. Does Does that answer the question?
Yes, thank you.
Thanks.
Okay, so he confirmed it answers, so sounds good. So, okay, any more questions to our speakers in the last session? Okay, if not the case, I would like to thank you all of you again. Really nice talks. I mean, coming from different, how to say, research areas, and that's really interesting. We see how ML can really empower different, how to say, very different research areas. Okay, thanks a lot, and thank for all the attendees for staying until the last minute in our session. And with this, I would like now to pass it to Ulf. Now, I think, Ulf, you hear me?